quiz on Monday over substitution and mass spec. If there's no questions, we'll proceed with elimination. First page, there's an elimination here. If you look at compound 63, 1 to 64, it's an iodine here. Illustrates an elimination here in the synthesis of Tamiflu. It's a multi-step synthesis, number of reactions ultimately leading to Tamiflu. Eliminating here by an E2 mechanism. What are we doing? We're making an alkene. Elimination reactions typically give alkenes. Way to make alkenes. Okay? More generally, pi bond. Most commonly for us, it's going to be a carbon-carbon pi bond, thus alkene. What are we eliminating? We're eliminating the iodine, it's gone, but also an H from this carbon, which is next door. That's called the beta carbon. The leaving group is on the first carbon, the alpha carbon next door beta. Removing that H. We're eliminating HI here. We're removing HI from the compound. This generates a pi bond, generates an alkene. So, it's actually the reverse of addition reactions, because if you take this and you add HI, you come this way. And that's like an alkene addition reaction. It's the reverse of addition. Okay, let's get into this. Consistent with substitution, it's leaving group chemistry. You got to have a leaving group. Okay, leaving group chemistry. We talked about leaving groups, yeah? What are good leaving groups, etc. How do you make OH a better leaving group, etc. All that applies here too. Okay, it's the same leaving group considerations. Going to be called beta elimination because we're removing the beta hydrogen. What type of carbon do we eliminate from? The leaving group leaves from what type of carbon? Tetrahedral carbon. The leaving group does not leave from a sp2 carbon, not in these mechanisms. Okay, general line reaction. We're going to have a tetrahedral carbon with a leaving group. Okay. We're going to have a base. Now with substitution, we had a nucleophile. What's the difference between a base and a nucleophile? Not much. Nucleophile attacks like a base attacks what? H. I mean, otherwise, it can be the same molecule. We call it a base in this situation. We call it a nucleophile in this situation. I'm calling it a base here because ultimately it's going to attack a proton, an H. Okay, we do a beta elimination. We can remove the leaving group. We're also removing an H from here. There's two there, but one of them gets removed. We're eliminating HX. Sometimes this is called minus HX. That's sort of formally what's eliminated. The hydrogen and the leaving group, we're going to have to put in a double bond. The X leaves with the lone pair. The base takes the H. I'm not showing any charge here. The base may or not be charged. The X, the leaving group, may or may not be charged. All right, that's a general line reaction. This can also be called dehydrohalogenation. Because what are we removing? We're removing a hydrogen and a halogen. Assuming the leaving group is halogen. Now, if the leaving group is something else, then it's not a dehydrohalogenation. It's something else. Because you can't have leaving groups other than halogen, right? Okay, let's look at a specific example. You take this alkyl bromide and you treat it with tert butoxide, T-butyl oxide, or it's called tert butoxide. We can get a beta elimination reaction. Right? We're removing HBr, essentially. Now, we don't generate HBr, but that's what we're removing. Okay? We actually generate Br minus, the leaving group, and the base took the H. Just like we said above. All right? So, there's two possible mechanisms we'll see for this. Just like with substitution. We're going to call one of them E1, the other one E2. There'll be similarities. Okay, what can we do here? E1, what's the first step of an SN1? Leaving group leaves. It's the same as the same first step of E1. Leaving group leaves. Okay. I tell you here, ionization, that's right turn. Okay, this leaves. It's got to leave, right? Doesn't it leave? I mean, we generate Br minus. How can we generate it? That can leave. What does that give? Gives that plus what? What's that? There's one product we made. How are you liking this mechanism so far?
Trash.
Okay, why?
To give you a primary carbocation.
We made primary carbocation. Not good, right? But still, this is E1. E1, you make carbocation, just like SN1. Okay, how do we define our products from here? There's two H's here. Now for SN1, then this thing attacked the cation, and we got an overall substitution. And this thing was now bonded here. In elimination, instead, this thing is going to act like a base instead, and these electrons bond to the H, and these two electrons fall in here and make pi bond. And what does my arrow movement do? Fall in here to make pi bond, gives alkene, plus what? That takes the H, and now the base has the H.
Wouldn't it be better if it was concerted code?
I mean, the overall mechanism? Yes, that's down below. We're going to do E2. Yes, yes. This is not the mechanism for the model reaction, but I am illustrating E1. What's the rate determining step of this mechanism if it were to happen? Yeah, it's just like SN1, forming the high energy carbocation. Right? If we did a reaction coordinate diagram, we can do one here, yeah? We start with the alkyl bromide, yeah? We form the high energy carbocation, and then we come back down to the alkene. We can talk about thermodynamics. Is the alkene more or less stable than what we started with? Actually less stable. Why? Because we actually went from 2 sigma bonds to a pi bond. 2 stronger bonds to a weaker bond. Elimination reactions are not thermodynamically favored. So can you do them?
Use heat.
Yeah, you can do them. Okay? That is supposed to be higher than this. So it's in endothermic reaction, yeah? Okay, here we go. We have a transition state leading to the carbocation, then we have a transition state leading to here. But you're following downhill, right? It's the same old discussion. What's the rate determining step? Forming the carbocation. Okay, of the two main reactants, which ones are involved in the rate determining step? Is that involved in the rate determining step?
Yes.
Yeah, I mean, leaving your let leave. Is this involved in the rate determining step?
No.
No, that's the rate determining step. That is only involved in the next step, which is fast. Only one of these is involved in the rate determining step. That's why it's called E1. Unimolecular mechanisms.
Can't BR go back and take the H instead of the,
Can this take the H?
yes.
It theoretically could.
So wouldn't it be closest at that moment in time? Because it just been kicked off.
Perhaps. Part of the main question, which is a stronger base, this or this? I mean, that's just like hydroxide. Hydroxide or Br minus? Butoxide, yeah. Why do you ask this question?
Because it's also, I mean, it seemed like it was had an equal chance of taking.
Okay, but you haven't seen anything or read anything, you just are thinking this on the spot? I mean, okay, I just wonder where you, maybe you're coming from something. Eventually, we may point this out. Yeah, it's very reasonable. If this took the H, you would make the alkene plus what?
HBr.
Plus HBr. And we'll see a reaction like this, yeah. Here we have a base. Okay. All right, this is an E1 elimination. It's not the mechanism for our example reaction because we would never want to form a primary carbocation. It is an endothermic reaction. Can it take place? Yeah. We said you can't do endothermic reactions. You can. You just need heat. But guess what? You need heat to do an SN2. You need heat to do a lot of reactions because that doesn't correlate with being endothermic or exothermic. I mean, this could be exothermic. You still need heat. Why? But you still got to form a. You still need to form an intermediate. I know some of you guys think an exothermic reaction doesn't need heat. No, that's just not right because the rate determining step may require the heat. Overall, it may be exothermic, but the heat required to make it go, and then you release some heat. But entropy, though, this reaction is more driven by entropy because one molecule is going to two. If you just look at it's eliminating. Eliminating means it's here and it's. If you eliminate something, it's becoming two things. Right? And you are generating more molecules, so that's driven by entropy. But it's not driven by enthalpy. Okay, let's look at another mechanism for this. E2. So, also sort of tell you here, now it's going to be concerted. Another way to get to this is, okay, Br is not going to leave. That's the answer. If you don't want to form a primary cation, you're going to say that the Br can't leave, right? Okay, if the Br can't leave, how can we do this? What's another way to do this? Well, another way is for this to just take the beta hydrogen. These electrons move in here and expel the leaving group. And what does all that air movement give? It gives that. And it was a concerted beta elimination, all in one step. There's no intermediate in the elimination here. It's just a transition state. The transition state consists of this bond taking the H, this bond being having, this bond breaking, this bond moving in, that bond breaking. All these bonds breaking and making at the same time. There's a transition state there. No intermediate here. No carbocation intermediate. For the example reaction, this is the mechanism. What's the rate determining step here? That step, because we only showed one step. Rate determining step is, that's it. Of these two, which are involved in that step? Both of them, they better be. If it's only one step and they're both reacting. 2. Okay, bimolecular. It's called E2. Elimination bimolecular. The base takes the beta hydrogen. Is this H acidic? No, it's not acidic. How is it able to take it? Well, it's part of the elimination. It's not acidic. Okay, I think on the next page there's a, so this is called an E2. This is the mechanism for the model reaction. You would never say this reacts by an E1. First step of an E1 is the same as an SN1, making carbocation. Another possible mechanism. I showed 2. Does anybody have a third? Can we do this another way? I showed one that formed an ionic intermediate, carbocation. I showed one that formed no intermediate. Could we show another mechanism? What's another way to get to these products? All right, let me show you another possible mechanism. We got H's here, these beta hydrogens. What if this just took an H and left the electrons there, like a traditional acid-base reaction? That would give boom, boom, boom. Make anion. All right, there is another H there. Plus that. There's that right there. Yeah? We made an anion here. Did we make an anion in our previous mechanisms? No, so this is a different mechanism. How do we get to final products from here? Now these electrons move in and expel the leaving group. Okay, so this is a third way. Well, this way, I'm not giving you a name. We'll never look at this way again. The reason I point this out is because some of you will want to try to do it this way. It's not the mechanism for any of the elimination that we're doing. Because this H is not acidic. That's just a hydrocarbon H. All right? We're never going to do that. This is a possible mechanism in some cases when the beta hydrogen is acidic. But that's going to be very rare, and it's never going to happen in this class. Okay? We made a carbanion here. We're never going to make a carbanion again in the elimination reactions we do. Let's look at this here. Question, in the previous two, in the E1 and E2, in which of those did the leaving group leave in the rate determining step? E1 or E2? Both of them? E1? E2? Yes. Leaving group leaves in the rate determining step in both of them. What about this mechanism? What do you think the rate determining step is? Probably forming the high energy anion. And then from there we go downhill, fast step. The leaving group leaves in the fast step here. Because it leaves in the fast, leaving group is not as important. The ability of the leaving group. Okay? You may see this mechanism in organic too. The main thing I'm pointing out is, do you know when the leaving group leaves? Fast step or rate determining step? All right? In E1 and E2. What about SN1, SN2? Leaving group leaves in rate determining step in which mechanism? Yes, both. Okay? So we'll never look at this type of mechanism again in this class. We'll only be looking at E1 and E2. Okay, let's look at another reaction. If you take this alkyl bromide and heat it with this alcohol, not an anion, but just alcohol, or no solvent at all, you get this alkene plus HBr. First off, what type of reaction is this? There's only about 5 types of reactions in organic chemistry. You have addition, elimination, substitution, rearrangement, and maybe another. What type of reaction is this? Elimination, right? We eliminate HBr to give this, and there's what we eliminated. One molecule went to 2. Here you can clearly see the entropy I talked about. Entropy is going to be favored here. But not enthalpy, because we're going from 2 sigma bonds to a pi bond. And you can do your calculations. It's not going to be favored by enthalpy. But you can still do elimination reactions, yes. Okay, mechanism here. One thing we can say, SN2 requires what type of nucleophile? Strong. Correspondingly, E2 requires a strong base. Okay? What about base? In which mechanism, E1 or E2, in which mechanism is base involved in the rate determining step? E2. Thus, it needs to be strong. All right? You only do bimolecular reaction if you have a strong nucleophile or a strong base. What's a strong base? Same as nucleophile. Anions or sp3 nitrogens? Okay. Do we have a strong base in this reaction? No. Only thing I see is an alcohol. That's not a strong base, is it? Okay. So that right there eliminates E2. This is an E1 mechanism. What's the mechanism? First step? Leaving group leaves. And carbocation plus Br minus. What could take the beta hydrogen to put in the pi bond? Well, to show what we showed here, yes. Br minus can take VH. We're going to have to see something here, but that would give that, right? And the alcohol really did nothing in this reaction? Or maybe it just served as solvent. Yeah, this is an E1. Because an E2 elimination requires a strong base to do that concerted elimination. I've been waiting on it. Question?
Is there a reason that alkenes trans?
Thank you. I was waiting on it. I was kind of waiting, giving a few seconds for that question to come. Thank you. Yes. Why is this trans? Good point. We need to talk about that. Would you expect it to be trans or cis?
I would think it's this.
Why cis?
The confirmation is kind of system.
Yeah. That's a single bond, free rotation, right? Okay. Is this going to prefer to exist like that?
No.
What do we have here? Like this? Consider that cation. Is that going to exist like that or will it exist like this? Like this? Yeah. Of course. What did I not show here? Well, this thing is probably going to rotate. Right? I mean, what is that? That's conformations, right? We talked about during test 1. Which conformation is preferred? Left or right? Over there. I mean, the equilibrium here is like this. And really now the Br minus takes the H. Electrons move in, and we get that product. You'd expect the trans product. Yeah? So we did see cases with Br minus 2pH, yeah? Yeah. Or no solvent at all. You don't even have to have a solvent. If you take this compound and just heat it at a high temperature, okay? Like at about 200 to 300 degrees. Problem is, can you practically do that? Because it may start boiling and then you just lose it instead of it doing any chemistry. But at a very high temperature, it will decompose. What does decompose mean? Break apart. It'll break apart. It'll eliminate HBr. By what mechanism? It'll just ionize and then the Br minus will take an H. You get this. You heat this at a very high temperature, it may start giving off a gas. HBr. They start decomposing by an E1 mechanism. Because heat is going to favor the entropy-driven mechanism, right? Because doesn't temperature magnify entropy and gives free energy equation? Yes, heat's going to drive it to the entropy side. By the way, can it go the other way? Can an alkene react with HBr to give an alkyl bromide? So we did lots of that during test 2, right? And we call that an addition reaction. Elimination reactions are the opposite of addition reactions. What's the mechanism for going this way? Alkene attacks H plus to give what? Carbocation? Where would you make carbocation? Left or right? Either. It's actually the same cation here. And then what happens to the cation? Br minus attacks cation. The mechanism is just the opposite. It's just the opposite. To do a addition. And it's actually an equilibrium. Which side's favored? I mean, can these two react to go that way? Yeah. It all depends on how you're doing the reaction, because if you're heating this and you're doing this way and this escapes into the atmosphere because you're driving it away and the gas is leaving, then it can't go back because your HBr has escaped. And you're just left with that, and then you can just have that. That's how you drive an equilibrium. If you want it to go that way, you come back and you add lots of HBr and you sort of drive it the other way at lower temperature. Question? Okay.
Why would the bromine take the H if it's not a strong base?
Good point. This is a fast step here. Let's get rid of, in this mechanism, what's the rate determining step? Yeah. Good point. The base is acting in the fast step. And since it's a fast step, it's an easy step. And since it's easy, just about anything can act as a base. Yes, weak base. Because if it was a strong base, we'd be doing E2. This is also the thing. This is essentially a positive molecule. The Br- is taking H from a positive molecule. You'll never see Br- taking H from a neutral molecule. Okay? Taking an H from a positive molecule is much easier because it's going from a positive to a neutral. Where in the E2, the base takes an H from a neutral molecule. Much more difficult. It has to be a strong base to do that. Okay, thermodynamics, entropy, we already talked about that, right? Okay, when Regio Isomers are possible, okay, next couple of pages we're kicking it up a notch. Some detailed stuff here. Applying some of our previous knowledge. Okay? All right, let's look at this. Some of the more intricate details of elimination reaction. Possibility of Regio Isomers. Look at this. If you take this alkyl halide and do a beta elimination, it's most likely going to have to be E2, right? Because you're not doing E1 here. Primary. Okay? All right? There's only one alkene possible. I'm just going to draw one hydrogen in, okay? You take this H, and you put the double bond in between that carbon and this carbon. Only Regio isomer possible, the only region where the double bond is going to be. And by the way, there's only one stereoisomer possible, because that alkene is not stereogenic. So that first reaction, if you are said to do an elimination reaction, that's the only product you can show. On the other hand, if you take this compound and do a beta elimination reaction, there's actually 3 different structures you could show. First off, and what we're going to look at is beta hydrogens. I'm drawing in the beta hydrogens. We have one over here, and we can remove ACl and put pi bond in between these 2 carbons. And that would be that, which is the same as that. But in this case, we have a beta hydrogen over here as well. Because that's alpha, And this way is beta, but this way is also beta. We can also eliminate over here. If you eliminate over here, you're putting the double bond here. And these are Regio Isomers. The double bond's a different region. But for this Regio Isomer, it's stereogenic. You can have E or Z. It's also here. Okay? It's three possible products, theoretically. So down here, the question is, which one of those three will be formed? Well, it depends. You'd like to hear that, right? Depends on a variety of factors. Well, that's like a lot of things, including mechanism. Are we doing E1 or E2? Base used. What base exactly are we using? Orientation of the groups in the starting material. Do we have any original stereochemistry to consider? Okay, let's answer this. First statement. The most substituted alkene is called the thermodynamic product. Well, we already know that. Thermodynamic product. We looked at that one day about 20 after 8, and I told you we'll forget this. Okay, don't forget that. The more substituted alkene is the more favorable. We've looked at that several times along the way. Yeah. So that statement's nothing new. What's new here is if you're doing an elimination reaction, the more substituted alkene product is called the Zaitsev product. So when you do an elimination, that term is used. Now that's a chemist, Russian chemist, and nobody knows how to spell Zaitsev. Some people actually spell Zaitsev with a Z, like Zaitsev. Okay? Well, the most substituted alkene, aka the Zaitsev product, is always the major product in an E1. Always. But not necessarily in an E2, which can often give the less substituted alkene. And the less substituted alkene is called the Hoffman product. Go back up here. Of the three, which one's a Zaitsev product? Zaitsev's the most substituted, right? Which one? Both of them. They're Regio Isomers. I mean, not Regio Isomers. They're stereoisomers. They're the same substitution. Both of those are Zaitsev products. This one would be called what? Hoffman. That's your Hoffman product. The least substituted alkene. Okay? Uh-huh.
I know we said in the first example we are using E1, so are we using E2 in the second example?
First example, E1?
Yeah, didn't you say?
No. The very top reaction?
Yes.
That would be E2.
Oh, you said E2, not E1.
Well, would it be E1? E1 would be involved making a carbocation.
You're right.
You're not going to want to make a carbocation in the first reaction.
Okay. And the second one is also E2.
I didn't say anything about that one.
Can we say something about it?
Well, look at it. What do you think?
I thought E2.
The leaving group's on a secondary carbon. See, up here it's on a primary carbon, right?
Yeah.
On secondary here, is E1 more likely?
Yes.
It is. E1 is more likely. But, see, the second one, it could be either. Depends on what type of base. What if we use a strong base? E2. See, that's why I didn't discuss it, because we don't have enough information. The top one, though, we got enough information. Because I know A ain't going to form primary cation. So that's why I just mentioned it.
Could we form a cis alkene for E2? I know we said it's thermodynamically E1.
Can you form a cis? We haven't quite got there yet. We're going to be getting there. We got to answer this. All right. We just introduced Hoffman and Zaitsev terminology. Let's move on from there. Let's look at this reaction here. If you take this and with water, and by the way, it's probably going to need some heat. Okay? Probably going to need some heat. It's E1, right? Because it's a weak base. Weak. Or if there was nothing at all, that would also be a weak base. It'd be a no base. Certainly there's no strong base, so you can't be doing E2. So it's E1, right? Can you do E1 on this substrate? Yeah, it's not primary. Secondary is okay. Secondary carbocations are okay. They're not tertiary. They're not the best. Okay. This, if you eliminate, we're going to make this alkene. Okay? That alkene. Not, see, we got two choices here. There's a beta hydrogen here, and there's beta hydrogen here. We can put double bond in between here, which is this, or here. Okay? The other product, theoretical product, would be double bond here. Right? If HA, HB, okay? We're going to lose HB. This is if you lose HA. Which is going to be favored? This one or this one? Well, how do you answer it? First off, which one is Zaitsev?
More right.
That's Zaitsev. This is Hoffman. Okay? Right? What mechanism are you doing? E1? What was the statement about E1? I underlined it. Whenever you're doing E1, the major product is always the Zaitsev. Okay? Zaitsev. Now, is this product stereogenic? Do we need to worry about E or Z? No, that product's not stereogenic. So we're done. Zaitsev, done. Summary. E1 always gives the most stable alkene as the major product. Zaitsev is the most stable. Why does it always give the most stable? Because it's really thermodynamically controlled reaction. It's really almost an equilibrium, and the most stable is just favored. It's almost just sort of the default answer. Okay? Because basically the transition state leading to a more stable product is going to be lower, typically. And that's the reason. Ultimately, E1 is easy. Go back up to that one, and there's three products. If that was E1 mechanism, which of the three would be the product? Which of these three would be the product if it was an E1 mechanism? Which one?
The middle one.
The middle one. Why? First off, it's di-substituted and not mono-substituted. But you got two di-substituted. Which one's most stable? E, with the groups trans to each other. That's just like this. Which is more stable, that or this? That. See, this has free rotation, so it's not two different compounds. That's just rotamers. That's two different compounds, but still it's the same answer. I show you two, one with the groups opposite or one with the groups like this. It's the one with the groups opposite. The bigger groups. Okay? Here the two bigger groups are on the same side. That's your E1 product. The E2 product can vary. Okay? E2 product can vary. Let's look at that example. If you take the same substrate, but react it with hydroxide, and so now we have a strong base, and thus we're doing E2 if we're doing elimination. This will give the same product, thermodynamic product. Now we're about out of time, so let me just sort of talk general here about this, and we'll pick up here on Monday. On the other hand, if you use a sterically hindered base, bulky base, the major product is going to be the Hoffman product. Okay? That is, they're both going to be E2 because they're both strong bases. But a sterically hindered base leads to the Hoffman product, which is called the kinetic product. It's not the most stable. That's a monosubstituted. That's tri-substituted. And your answer is because of sterics, the base is involved in the transition state in an E2. And this H is more accessible. This H is sort of hidden up here between these two methyl groups. Okay. We'll pick up here on Monday. After the quiz. And so in lab, we are doing a